now, and I'm going to start with this optimization methods lecture now, and we'll talk a little bit about a certain mm, uh, vector analysis and functional analysis theory part. It's just a few minutes, mention some of the concepts that we will be using. So it's not going to be very demanding on you. So we mentioned this, I wanted to mention this because we talked about bounded linear operators. So the idea of a bounded linear operator is simply this, that when you apply the linear operator on something, on an object of your vector space, you get an object of another vector space. So if you think about this, think in terms of matrices. Matrices are always bounded. There's no problem with matrices, but there are unbounded operators for more complicated spaces. But the normal garden variety matrices, those are always bounded. There's no problem there. And because of this, the bounded linear operator has a norm. And it means that basically you can define it in various ways. But one way to define it is just take the subprimum of all the vectors of length 1 or shorter, apply that linear operator to that, and see how big that vector becomes. I mean, or if it's a scalar, then how big that scalar is in terms of absolute value or norm if you're dealing with vector spaces. So if you want to think about this in real spaces, real valued spaces, Rn, then the matrix norm is basically simply, if you take a vector, you multiply it with a matrix, and mostly we can think we can think that we are it's a square matrix, because I mean, we will be talking about the second derivative. So our second derivative is going to actually be a square matrix. So it means that the norm of the matrix is simply the length dilation or subtraction, the maximum length of a unit vector when you multiply it with this matrix. Because a matrix, what it does rotation and scaling of vectors. And basically that's all it does. I mean, everything a matrix does can be thought of as a rotation according to certain axes, and then scaling of certain axes. And basically the matrix norm can be thought of as the maximum scaling across all of the axes it operates on. It's not going to be, we're not going to be needing the matrix norm. I'm just saying that when the operator is bounded, we can define this. If it's not bounded, if it's unbounded, then some of these vectors will have, they will blow up to infinity, or, meaning that for those it's not actually defined. Okay, that's your takeaway on linear operators. You can think of a linear operator as a matrix, really. And then we talk about bilinear operator. Well, a bilinear operator has not one, but two arguments in it. So if you think of a linear operator as a matrix that multiplies a vector, and think square matrix if you want, so that it rotates and elongates it, or if it's not square matrix, it just maps into a higher or lower dimensional space while doing some rotation and scaling. But a bilinear operator, you can still think of it as a matrix, but now in our situation, the target space, or the codomain of this operator in our situation is always the real numbers. It can be in other situations, a bilinear operator can have an arbitrary space as its range, but in our case, we can think of it as a mapping from Rn to R. And it's bilinear because it has two arguments, two parameters. And if we think of this in terms of matrix, it's matrix multiplied by a vector from the right-hand side and from the left-hand side. And this is just a linear operator, but it's now a bilinear operator, meaning that it's linear in both. Linear meaning that if you multiply this with something, the result will be multiplied by the same thing. If you multiply the other argument with something, the result will be multiplied by that. If you take this vector and you add something to it, so you're from the left-hand side or the right-hand side, you're multiplying the sum of two vectors, then the result is apply the linear operator to x plus apply the linear operator to y, and it's still the same. So you can separate all the sums and products. So this is in next week's exercises, and you can think of this if you want as matrix multiplication from left and right, and if you want to, you can think of all the places where it refers to bilinear operators. You can think of a bilinear operator over x and y is simply a matrix A such that it's x transpose A times y. So I just write it like here. So the bilinear operator of x, y is simply x transpose A, y. So it looks like this, where this A is some matrix. And depending on the dimensions, I mean, the space here and the space here can be different because this may be not a square matrix. But in our cases, it's always a square matrix and the result is a real number. But in many other cases, it may be some other space. But if it's easier for you to think of this in this way, think of this as a matrix being multiplied by both from the left and the right-hand side. And that's the bilinear operation. Here's a concept of isomorphism between spaces. I wouldn't need that. It's just that if there's a bijection between two spaces, meaning that there's a linear, well, in this case, it says normed space, as isomorphic, meaning there's a linear operator that maps between these two spaces, and its inverse, maps back to the other direction. And if in addition to this linear operator has a norm of 1, really, basically, so that AXY is in fact the norm of AX in the space Y is the same as the norm of X in space X. We say that these are isometric spaces. Isometry means same length or same size. So, you can map 1 to 1 and the norm, that determines the space size is the same. So it's not consequential for what we are doing because all real Rn is the only real space that we're talking about. And there is no bijection between Rn and Rm when n and m are different. So we don't need to worry about that. I mean, if you go to functional analysis, there will be all these weird spaces that are not the same, but they are isomorphic and isometric and so forth, but we don't need to worry about those. I just wanted to mention this. You can read this theory if you are interested in this. This kind of theory is more in the realm of functional analysis. So I'm not sure if the basic course on functional analysis goes this far, but I think it should, probably goes about this far. And definitely the advanced courses on functional analysis deal with this kind of thing. So we're not going to be talking about this in this course, but I just wanted to mention this as something that we might need. And now I'm going to go to talk about the second derivative a little bit before we go to the material, because we're going to be needing it. So the second derivative is basically the derivative of the derivative. I mean, we have this situation where we have a function that is differentiable, and its derivative is a mapping that maps each point in our domain. It maps G to I. So everything in the domain of G is mapped into the linear operator. It's always a linear operator between X and Y. So if we are talking about from Rn to R, then this linear operator is simply a vector that together with the multiplication with another vector. So this is really this linear mapping that we get as a derivative, if we talk about Rn to R, is simply the gradient. And then the linear operation that we do is really the gradient dot product with whatever that it is that you are talking about, right? So that's the linear operator. The dot product is the linear operator, and the left-hand side has already been filled with the gradient. Now, this mapping that maps each dot in my space to the gradient, right, can be differentiable. Like now we're dealing with a mapping that maps a, I mean, this is linear operation, but you can think of this as just a vector. That is the gradient. So you can think of this f prime as a function that maps a point in my space to the gradient. So it's kind of creates a kind of vector field. Now, this mapping, if it's differentiable, then we have what we call a second derivative. And it's twice differentiable. And this can be thought of as a linear space. I mean, the isometry of these spaces it's mentioned there. So we can basically, that theorem states that we can just associate the first derivative with just a vector when we're dealing from Rn to R. And if we're dealing with the second derivative, we can just associate it with a matrix, n times n matrix. And the theorem that states here that if we have a twice continuously differentiable function, then the second derivative is a symmetric bilinear mapping. So in other words, it's a symmetric matrix. It's a symmetric matrix, and we call this matrix the Hessian. Okay, so this may be known to you, and the Hessian's components are simply the second derivative of this f. So you take the partial derivative with each of the component, and then you have the components x1 to xn, x1 to xn, and so in your matrix, entry ij is simply derivative with respect to xi, and then a partial derivative of that with respect to xj. And because of the derivative, partial derivatives commute, you can take one in either order, then what you get is basically a symmetric matrix. So the Hessian is a symmetric matrix, and you can generate it with MATLAB commands. It's mentioned, we will rehearse this in the exercises. Now, the thing, there's a lot of things going on here. I'm not going to go in depth into this idea that is going on here. The theorem that states that twice continuously different, but this is still something that we're going to be needing, is that if you take the second derivative, then you can approximate the function even better. We mentioned that already. So this generalizes to a Taylor polynomial or what, but the constructs that you need to define it are far beyond what we want to discuss during this course. Also, there is a mean value theorem somewhere between x and x plus h. There is a point at which if you just take the second derivative there, then this whole error becomes zero. So we're going to be needing that a little bit. And I think, yeah, I think that's all we're going to be needing now. Okay, now we're ready to go back to the material at hand. So we're going to be talking about the optimization of this first, the optimization of the first in order to find the line or step length, sorry. So just as a recap, every single, and I tell you this, every single unconstrained optimization algorithm works in this way. You choose an initial point, that's your first choice. At each point, you choose the descent direction. I already mentioned this, a direction which you go to. It means that you want a direction which at least with some criterion, looks like the function is going to get smaller when you go in that direction. You determine the step length, meaning how far along that line you go. And then you just go that way and repeat until you reach the stopping criterion. So basically these four things are what determines what algorithm we are doing. And all the iterative algorithms that we deal with work in this way. So there are no other, I mean, you can, for all intents and purposes, you can think that there are no other optimization algorithms than the ones that follow this template. And really what we're going to be looking at are techniques and tricks in these issues. The initial point selection, we don't focus too much on that. There are issues there, and we will look at problems that arise when you choose the wrong or a bad initial point. But other than that, initial point selection is often something that we omit. Okay, just a very quick question. Is there any one of you who is studying, majoring in or studying currently for other reasons, some machine learning problem that has this error minimization or something like this? Is any one of you working on such a thing not right now because of some other reasons?
Well, at least I am.
Okay. Usually there are some people in here. Yeah. So most of those most of the algorithms applied in those situations follow this kind of template. Usually the initial point is something that, depending on the grander scheme of things, sometimes it's chosen randomly, or sometimes there are different ways of doing that. Okay, we can discuss this later. So let's get to our matter at hand. Now we talk about finding the step length. So let's say that we have chosen the direction dk. Look at the last line here. We've chosen the direction dk, and we're going to be trying to find a step length. How far should we go there? We want to solve this problem, minimize this. Really, we are dealing with this function, which may be really complicated, this f of xk plus t dk. But really, the dk and the xk are now fixed. So when we are just solving this for t, then this is just a univariate problem. And there are ways of doing this. We can find the derivative of this g by simply calculating the gradient of f at xk plus tk dk, and by finding a place where this goes to 0, we can minimize that and find a local minimum. We can apply the second derivative if we know the Hessian, and now notice how if we have the second derivative, the f has a Hessian. So basically this g is defined as simply there's an inner function t times dk, and then there is outer function f. So this is just the chain rule. The outer function's derivative is the gradient, and then the inner function, because it's t times dk, the derivative is simply dk. So we have this gradient times dk. And this, when we find the derivative of this, the outer function, this dk is simply a multiplier, so it remains here. We take the derivative. So in the inner function derivative, again, we take the t dk's derivative. It's dk, but because this is transposed, it becomes a dk transpose. And the Hessian emerges because as a derivative of the gradient. I mean, the second derivative, the gradient is the first derivative, so the Hessian is the second derivative. So with this in mind, we can try to find the 0 of this g prime. And here comes the Newton method. I mean, the Newton method you probably learned as a way of solving for the 0 of a function. So the usual way of this is to, so let's take a look at this. Just let's, for a little second, let's assume that our our G function G is, you know, there's nothing to worry about this. Let's say that we're talking about, I'm going to write this as, I'm trying to think of a letter that is not confusing. Let's call this Z of t, okay? So for argument's sake, let's say we are talking about Z of t. I have no idea what the Z of t is. I'm just looking for the zero of that. And let's assume that it's differentiable. So I'm going to use the approximation, approximate this using the derivative. So I have Z of t plus h, something like t plus h. I have no idea what that is, but it's roughly equal to Z at t plus, so I'm going to write this t, we're going to be iterating this, so I'm going to use tk. So I'm going to write here Z at tk plus h, and h is, you know, where do we go from this place? So it will be approximately that plus then Z prime times h. So this is roughly what we are dealing with. So when we move from tk to this place h, tk plus h, that's the next point, we have this. I mean, there would be the error term if this were equal to, but if this is a baby step, then it's roughly equal to that. And we're assuming that this h is so small that the error term can be neglected, right? And now we want to find what this determine this by what this h is really. So really this h is now so we're dealing with this. We just have to solve for this h. And okay, I'm not going to go in depth in this, how it's done. It's using this approximation here in the slide, G prime. Now that's going to be my new, okay, so it's written a little bit differently. Here use T, which is the ultimate point. I was just looking for the change in that. You can frame this T minus TK as my H here now. And now we solve this equation for this, this being zero, meaning that we are at a place where we are no longer having to move anywhere. And what we get here is basically we solve this for TK, T minus TK, so that would be the new one. So this T, solve this for T, and we get TK minus G prime over G prime prime. As I was going to do this with Z, but I realized that this is just as easy to pick from here. So we're basically solving this for T. And that's our new point. I mean, it's not going to be exactly equal to zero because this is only an approximation, but it's pretty close. So this is something that people learn in high school as well. So if we now rewrite this in terms of f, we have G is defined in terms of f. So we get the new point is the old point, and then there's the gradient, and then there's the Hessian, and it's multiplied with dk and dk transpose. So this can be continued until the stopping criterion is satisfied. It can be shown that this converges very quickly to the zero of the derivative, yeah. But this has the downside that of course, calculating the Hessian can be computationally heavy. I asked you guys if there's someone who is working with machine learning. So for instance, if you're doing neural networks and their parameters optimization, they have anything between thousands and millions of parameters to be optimized. Not necessarily millions, but let's say hundreds and tens of thousands in even the simplest applications. And if you're going to be tens of thousands of hundreds of thousands of these parameters, then that your function of your function, because you're looking for the weights of the network, then your X has dimensionality of tens of thousands. So the Hessian is out of the question. We can't really calculate the Hessian. We can maybe calculate the gradient, but not the Hessian really, because it's quadratic in terms of how many variables you have. There are other methods. We can approximate the Hessian by simply looking at how much did the gradient change when we moved, or how much did the derivative change when we moved last. So that's a pretty good approximation of the second derivative, is how much did the gradient change? I mean, because that's really what we're after. We're looking for how much does it change, so we approximate it by the second derivative. And you can express this without having to calculate the Hessian by, this is called the secant method. It comes from or the second, I don't know how you pronounce that, but it comes from the idea that, you know, if you have a curve like this, here's your curve, right? Then this line segment from one point to another, and this is supposed to be a straight line. This line segment is known as the secant or secant. I have to double check which way you pronounce, right? So instead of the tangent, which is right at that point, this is the secant. All right. So basically this is a univariate optimization problem, boils down to calculating the gradients and calculating the Hessians once more. If it's not differentiable or calculating this is hard, there are other ways. Literature tells us many ways to find a minimum if we know a bounded interval. If the function is the so-called unimodal, meaning that, you know, it goes down and then up, so it doesn't have a bumpy ride between this interval. So we know some intervals so that there it first goes down and then goes up. We can do an approximation. So this bisection method is fairly simple. So we just cut it into, I don't know why it's called actually a bisection method, because it's really what it is a trisection method. But really what we're doing is we are looking at certain slices, see if it's going down in this slide and up in this slide, then the optimum is somewhere in between. You know, we are looking for the point where it, to the left of it, it's going down, and to the right of it, it's going up. So we're looking for the minimum. Then, you know, this is the idea here is that you have these you move the endpoints, you know, either one endpoint or the other endpoint. So you're kind of forking it into the place where the minimum is. This is fairly simple. You basically have a parameters, which is the tolerance. This is how far you tolerate an error. And then there is this delta, which is, you know, how much you're going to be making your interval smaller. And then you have an initial interval. And then if your interval is so short that it's smaller than your tolerance, then you can just pick the midpoint and you know, you're close enough to the minimum. Otherwise, you take your delta and you take your midpoint, and then you find 2 points. Sorry, I'm going to draw this. This is something I want to draw. So you have here AK, and you have your BK here. I'm not going to draw the So you take some region around, so here's your midpoint, here's the minus delta, and here's the plus delta from the midpoint, right? Those would be your CK and DK. And now you're just looking at which one of these is smaller, right? And if this if the function at the CK is smaller than in here, then you move this to the left and this BK to the right, and this to the left. Sorry, no. You don't move this because this is smaller than that, then you move only this right-hand side. If this is smaller than that, then you move only this. So you are guaranteed that the smallest point is between these. If this is smaller, the smallest point is between these two. And you just keep on doing this until your interval has become so short that you are content that, you know, it's close enough if we pick the middle point here. There are ways in which we can then maneuver on how this midpoint is found, but this is also something of a very generic optimization technique. One that, I mean, if you are dealing with optimization methods, this is a very generic technique, because we're looking for the minimum in this interval. We know that the minimum is in this interval. We compare these 2 points. We make sure that the smaller one of these points is retained in the interval. So if this is bigger, we move this this side here, meaning that we are guaranteed that now the minimum is at this interval. This technique is very powerful if we know that it's unimodal, meaning there is an actual minimum. If there's a lot of wiggly wobbly things going on between here, then this doesn't guarantee anything. But if we know that there is some kind of a local minimum that is local, I mean, we're in a region where there is a kind of a global, you know, locally global minimum, then we can then use this method. And the interpolation methods here are not that important as the way of thinking, framing this here. Okay, all right. Let's now have a small, oh, there's a question here. I didn't notice. Oh, there was a question, when can exercise 2 be evaluated? I'll change that into the evaluation mode after this lecture, immediately. In fact, I can do it now. Let's have a small break, but I'm going to let you to do something. I'll have this pause recording on. So the gradient method refers to using simply the negative of the gradient as a descent direction. This can be characterized as the greedy method because technically, if you think about it this way, if you think of in terms of the directional derivative or the Gateau derivative, then the Gateau derivative is the most negative in the opposite direction of the gradient, because we already proved that the directional derivative can be thought of as the dot product between the gradient and the direction you are going. And to find the direction which has the most negative directional derivative is the opposite direction of the gradient. So the negative of the gradient it's guaranteed to be, at least locally, at least in some small distance, the direction where the derivative is the most, sorry, where the function decreases the most. Then it comes to solving the step length. So basically what we do is we have we've chosen dk as the gradient, and then we just have to choose the step length, and we have our new point. We already talked about choosing the step length or finding the minimum in this direction. In where, how far do we go? Let's first look at the theoretical properties of the gradient method. So one of the things that is beautiful in is that if we have a continuously differentiable function, that's C1 in Rn, and one that goes to infinity in all direction. If it's a function that goes to infinity, no matter how far you go, no matter what direction you go in, if you go far enough, the function will grow. There is why we need to have this is that there is a possibility that that there is like an endless plateau somewhere, you know, and like a flat surface that goes to infinity. And if we wind up on that flat surface, then the gradient method will keep us there, but there are no critical points necessary. I mean, no critical points there necessarily. And it's all but flat. Also, we can see some examples later on of that. But if this doesn't happen, so if it just, you go anywhere, it starts increasing, at least it goes to infinity in all directions. Then by going to the negative of the gradient, we're guaranteed to converge to a local minimum. It doesn't mean that or you know, a critical point at least. Doesn't mean that it finds the global optimum, but at least it converges to a critical point. A critical point being where the gradient is 0. The greatest weakness of the gradient method is a possible slow convergence. We'll see a lot of examples of this shortly when we look at the exercises. The thing is, we can show that if we go find an optimal step length, an optimal meaning we go optimize the step length here with this minimization 4.1. We minimize this GT, we take an optimal step length, we find a place where this f of xk plus t dk, we go in the direction of the gradient until such a time as the function no longer decreases in that direction. And if we do it this way, we can prove that the successive search directions are orthogonal, meaning that we go in some direction and then we move 90 degrees to some other direction, go there, do it again, and so forth. And this, if in certain even mildly pathological situations, leads to very poor performance of these gradient methods. If we go to the negative of the gradient, then the function doesn't need to be very bad or very pathological. It just needs to have certain features that look innocent enough. And your convergence will be terribly slow. I'll show examples of this. So the thing about, what about proving that the orthogonality of successive step directions? Well, firstly, assume now that this step on this current length minimizes the function f xk plus t dk, so that its derivative will be 0. And the thing is, it means that the derivative is determined as the current direction dk dot product with the gradient of f at that new point. And that will be 0. It means that the search directions have a dot product that is 0. So this means that the function will, you know, we'll see. I have some code that I'll show you in the exercises, but when you look at it, you move from one point to the next, and then you make a 90-degree turn, you move there and move like this. And this results in bad performance when there are certain phenomena at play. I'll show you examples of that. Let's take an example, the quadratic function. A quadratic function meaning it's, you know, Rn, we are dealing with Rn, and we have a second degree polynomial over n variables. And let's furthermore suppose that we can express it well, we can always express it in a matrix form, but let's suppose that we express it in a matrix form such that the matrix is positive definite. This means that the function is convex, really, because its second derivative is q, and that's positive definite. It means it's convex. Because it's convex, it means that a local minimum is a global minimum. If we can find the exact minimum, which is x star, we can show that the closer we get, then the closer we, well, it means that if we are at xk, and we're doing this with gradient method, and this is how far we are, then the next step, we are closer than m times the distance. So the distance is reduced linearly. However, this m is now determined by what is known as the condition number. If the condition number is large, it means that we are converging very, very slowly. We maybe if it's 0, if this m is 0.99999 something, then we are actually converging very, very, very slowly. So did you, now the question, you guys looked up, what is this condition number? What does the condition number of the matrix mean? Anyone can answer. I'm going to put a break here, so those of you who are watching this over YouTube have to figure it out for yourself. Okay, so technically what we were getting at here is really there are problems. There are problems related to the gradient method if the Hessian behaves in pathological or near pathological ways. So let's take a better approximation here. In the Newton method, if we have the second order derivative at our disposal, in the Newton method, we can approximate the function just like we did. So we are basically pretty close at an x where we're moving from xk to x, then in the direction of d. D is, let's say, we're moving from x and going to, xk and moving to xk plus d. So it's roughly equal to taking that f at xk, then taking the second derivative at, taking the derivative at xk times d plus 1/2, and then taking the second derivative and, you know, this quadratic form of d. There would be an error term there, but we're forgetting about this now. Let's call this mkx. So we're trying different points and see where do we end up. I mean, and now this really, this d is the direction or the step which we take. And depending on, so we're at xk here, let's say this pen is that d. We're going from here to there. This is our new x. And depending on what this x is, right? I mean, it could be longer as well, but, you know, we get different values, and let's call this mk. And we want to solve what this new x would be to make this.
Sorry to interrupt. I can only see MATLAB window on the screen.
Okay, thank you. Thank you for noticing. Thank you. I accidentally forgot to press. Thank you for mentioning. So you see the Newton method here. So we're moving from this point to this point. Let's call this d. And let's call this value of the function at the end of this as mkx. Varying this x to different places, right? Like this. We get different values. But honestly, that's just an approximation. That's not the true value of the function. It's just an approximation based on knowing the derivative f prime and the second derivative f double prime, or the gradient and the Hessian. But let's look at that. So this mk at x is a function on its own, right? It's the approximation. We calculate its derivative, meaning its gradient, and we set that to 0. So when we take the derivative of this with respect to x, we get basically this is the gradient of f at xk plus the second derivative at xk times operating on x minus xk. And we set that to 0. So we get that this x is now xk minus the inverse. We have to set this, we solve this for x. So let me just rewrite this. So we have this, I'll write this in text. So you get there. So I have we have established that the gradient of mk is at x is the gradient of f at xk plus the second derivative, that would be the Hessian at xk operating on x minus xk. And we set that to 0. That's what it says on this is what it says now here. So if we solve this, I'll do that one extra step. So we get here that gradient of f xk plus operating on x so we have this, right? And now we solve it for x, and we get f prime prime x minus, so equals so we solve it, so we get that on the right hand side we have f prime prime operating on x is equal to f prime prime operating on xk minus the gradient of f at xk. And now we multiply it with the inverse of the Hessian, inverse of the Hessian, and we get that x is equal to xk minus f prime prime xk inverse times the gradient at fk. So the thing is, if we calculate at any point, we calculate the gradient and the Hessian, then simply using this rule, we get the next iteration. No step length involved, actually. We're just directly solving using the second derivative. We're solving the next point. So the step length is, basically you can say that the step length is 1. Okay? So this is Newton method in the sense that we're basically basing this on the second derivative and finding the next point. So the problem here is that here, of course, this inverse times the gradient is of course always computed not by taking the inverse but solving this equation. The reason being methods like elimination method that solve this equation are numerically more stable than the ones that calculate the inverse, especially if we are at points that are closer to singularities of the Hessian. The Newton method doesn't converge globally, but there are theoretical results that give us a good results. If we say if at this optimum point this Hessian is positive definite and it has this so-called Lipschitz continuity around that point, then the method converges if we are sufficiently close. Lipschitz continuity is an important concept needed elsewhere. It simply means that when we move from one place to another, there is a limit as to how big a proportionate change occurs in the function. So if we move from x to y, then if the norm of the change in the function is bounded above by some multiple of the change in the norm of between x and y. So there is not the possibility that getting closer to a certain point, the proportionate change goes to infinity, right? Situations where this might occur, that this might become a problem, are functions such like let's take the cube root. I mean, this is just a real-to-real function, but it has a problem with Lipschitz continuity because a cube root, you know, it approaches 0, and it's defined also for the negative values, but it has actually the derivative is approaches infinity at the origin. So if you calculate that, it looks I'm bad at drawing, but it looks something like this. So when we are very close to the origin, a small change left and right direction has no upper bound on the proportionate change of the function. So a cube root, for instance, is an example of a function that at 0 is not Lipschitz continuous. It's continuous, but not Lipschitz continuous. Because if you are very, very, very close to 0, getting very close to 0, you know, and you move by a very small epsilon, then if you take this, the function changes very, very much. You know, if you divide it by that epsilon, it means simply that the derivative approaches infinite. I mean, if you have infinities of the derivative, this would mean that the third derivative has infinities in it, if it's not Lipschitz continuous. But we can't really talk about third derivatives here. It's not exactly the same thing. I'm just trying to give you the intuition here. So the thing is, if you have a very difficult and very pathological problem, if you're going to use the Newton method, the initial guess has to be very close to the true minimum. Otherwise, the method might diverge. We'll show some examples of problematics here. But these are the two methods, go-to methods in most literature and in most applications. One problem with this Newton method is that, well, there are many problems, but one of the problems is that if we are at the point where this the second derivative or the Hessian is not positive definite, then we run into trouble. If it's not positive, if the Hessian is not positive definite, then the direction we go to might not be a descent direction. We may end up increasing the function. This means that we may get convergence to a wrong point. And this is not actually an uncommon occurrence. I mean, we will see examples in the exercises of situations where this Hessian is not positive definite, and this, consequently, the algorithm will not converge. One way to make this a positive definite, remember, how do we say that it's positive definite? Well, one way to say is that it's all its eigenvalues are positive. One way is to modify the Hessian. And one way to do it is by just adding stuff on the diagonal of the Hessian until such a point that this new modified Hessian or this modified matrix is positive definite. This would guarantee that the search direction is at least a descent direction. There are other tricks like what is known as the generalized Cholesky factorization. I'm not going to go in there, but I'm going to give you an example to do in groups. Let me just see. And okay, I'm going to pause this. I'm just going back. So this is an easy fix to changing to adjusting or modifying the Hessian. It's an easy fix to just add something on the diagonal as long as you get a positive definite. The idea here is to guarantee that if you're going to sorry. Sorry, yeah. The idea here in modified Newton's method is that if you're going to be multiplying the gradient with a matrix, then it should at least be such that go to the negative and not the positive direction. I mean, take the negative of that. This modified Newton's method, meaning that you find a modification on the Hessian that is guaranteed to be positive definite, it converges globally. It's far superior to the gradient methods because the gradient method has bad performance when we are in terms of convergence. The Newton method has a very good convergence result as long as it converges, but it has problems with the situations where the Hessian is not positive definite. So that gives us the possibility of taking advantage of both methods. So basically, as long as we're dealing with a region where the Hessian is positive definite, then this modified Newton method simply works as exactly as the original Newton method. And when we enter a region where the Hessian is not positive definite, this takes into account partially the information in the Hessian, but also guarantees that we overcome the problems of singularity, but also the problems of negative, not necessarily having positive definiteness in the Hessian. It says here that provided that the second derivatives are easy to compute. So the caveat here being that if you have a low dimensionality, so the number of variables is not huge, then this is fine. But in many modern problems, especially those appearing in like, let's say, neural networks or somewhere where you are optimizing, finding the minimum classification error or something like this, the dimension is very large. So the problem is not that the functions are hard to compute. In fact, in most neural networks, for instance, the activation functions are specifically designed to have a very easily calculated derivatives and also easily calculated second derivatives. The problem is the Hessian has these second derivatives. If you have n variables, then the Hessian has n squared entries in it. And even if it's relatively sparse matrix, this can be very large indeed if n is very large. So we'll look at, next we'll look at some methods in which the Hessian is too hard to compute, at least on every iteration, right? So we'll look at that tomorrow. The idea of the quasi-Newton method is to have something that is pretty close to being equal to the Hessian without having to calculate the second derivatives every time over, because the second derivatives may be too hard to compute. All right, I'm stopping here and we continue tomorrow.